Um, I'm just speechless by how smart everyone in this room is. These presentations are amazing. And it's an honor to be a part of this organization. This is my first time mentoring for Magic. My name is Michelle McNulty. I am a computational biologist at Boston Children's Hospital. So came here to New York to be here today. And it is my absolute pleasure to introduce Emily Pang. She is a brilliant 11th grade student at Marymount. Um, I study genetics and I use R programming language. And she came to me wanting to do something related to space or astrophysics in Python. So needless to say, I've been learning a lot alongside of her, which has been absolutely wonderful. And I know more about exoplanets now than I ever thought I would know. Um, I'm truly inspired by her, impressed every week we meet, and I'm really excited to keep up with her after this and see what's in store. And yeah, Emily.
Thank you. Yeah, so as Michelle said, my name's Emily. I'm an I'm an 11th grader from Marymount. Next slide, please. Okay, so my mentor is Michelle McNulty. As she said, she is a senior informatics data scientist at Boston Children's Hospital, which means that she works a lot with coding and specifically R, which is relevant later in the project. And she's currently studying the genetics of pediatric kidney disease, and hobbies include photography, staying active, and watching musicals, which we bonded a lot over. Next slide. I would also like to thank Emily Rice, who is an astronomy professor, for giving us additional background information and project inspiration. Thanks. Next slide. So the topic that we chose for my project was astronomy and specifically exoplanet discovery. So what is an exoplanet? An exoplanet is just any planet that's not in our solar system, and exoplanet discovery is really useful to find habitable planets and also maybe even to find life outside of Earth. The first NASA mission that launched expressly to find exoplanets was the Kepler mission, which launched in 2009, and it found planets by detecting planetary transits. As you can see here, when a planet passes over its sun, there is a dip in the light curve, and that's how Kepler found these planets. Next slide, please. So my project was to create a machine learning algorithm on Python to determine whether or not an object identified by the Kepler telescope was or wasn't a planet. And from this, I really wanted to learn how to use Python for data analysis, especially as technology and machine learning becomes more prevalent in science research. And I also wanted to understand astronomical data more. I think astronomy is super fascinating. There's just so many possibilities, and the world is a lot bigger than we think it is. Next slide, please. So the data that we used is publicly available on NASA's Exoplanet Archive. There's a lot of rows, a lot of columns and variables. The most important variable is the one titled dispositions, which there are three dispositions that each object was labeled. It was either confirmed, which means that it was a planet, a false positive, which means that it wasn't a planet, but the Kepler mission saw something, but it was something else. Like maybe it was two binary stars. That was the most common false positive, or maybe it was background noise. And then there were also candidates, which meant that NASA saw something, but wasn't sure whether it was or wasn't a planet. And so from this, we were able to say, well, we know how the data of the we know how the data of the confirmed planets look, and we know how the data of the false positives look. But which one does each candidate look more like? On screen is an example of one plot of one variable, which is the planet star radius ratio. And as you can see, there is a really strong relationship in between being a false positive and having a higher value. But again, this is only one variable of many. So our main issue was how do we to take a look at all the variables to make a decision. Next slide. So the answer to that is machine learning. So machine learning learns from a set of data to make predictions on new data. And specifically, the algorithm that we used was logistic regression, which predicts a binary outcome from quantitative data, which means numbers basically. And it weighs variables by giving each variable a coefficient to make a linear sum, and then applying a sigmoid function, which basically gives it a probability on a scale of 0 to 1 of how likely an outcome is. Here, 0 would be a false positive, and 1 would be a confirmed planet. Next slide, please. So first we had to sort and filter the data to make sure it was ready to be trained upon. So in the original data set, there were a lot of columns that either had that were entirely missing data. So we removed those columns. And then there also were several columns that provided too much information. For example, there was one variable titled KOI score, which basically was like NASA's confidence rating on how confident it was that something was or wasn't a planet. So that gives the answer away. So not useful for training. And then as you can see here, there also were several there were several observed objects that had missing data, which we filled in using imputation. Next slide. So imputation is basically making educated guesses to fill in those empty spaces based on everything else that's available from the variable. And then because we were curious to see how imputation impacted prediction, so we isolated the imputed data from the complete data. Next slide, please. And then we further split up our data into candidates and false positives and confirmed, because again, our end goal was to make predictions on candidates. Next slide, please. And then lastly, we split our false positives and confirmed into a training set and a testing set. The split was 80% training and 20% testing, and it's for exactly what you think it would be for training and testing. Next slide, please. So this is a look at my code and like everything that I was saying earlier about filtering data and taking out rows and imputation. But the important part is here where we train the data. So as you can see, we use a function called logistic regression, which does logistic regression. And importantly, we use things like elastic net, which accounts for covariance. And covariance is when variables share like say really similar things about the data and they're highly correlated. So it's basically telling the algorithm not to account for that data twice. And then also max iter, which here we set to 10,000. And it allowed our algorithm to iterate enough times to allow coefficients to converge, which again is really useful. It increases accuracy. And then I also made a plot to show our top 10 most important features. The main takeaway here is that out of the top 5, 3 of them were false positives. And initially we had were false positive flags. And initially we had concerns that that these false positive flags gave too much information, like KOI score did. But we eventually chose to keep it in. And our choice was validated by a paper that we found online that also investigated Kepler data and left in the false positive flags. Next slide. And then so our results. So as you can see on the left, we tested our machine on the training set, and we found that it was roughly 98% accurate, which is really high accuracy. It was significantly less accurate on the imputed data, coming in at around 72%. Though it should be noted, which makes sense because a lot of the data from that set was what's filled in and not actually relevant to each object. But it should be noted that of the imputed data set, only 13 of them weren't planets. So we were curious. So like this could be something to investigate later on as to why so few so few of the imputed data set had missing were not planets. Next slide. And then lastly, we tested our algorithm on the candidates, and we found that our model said that 83% of them were real planets. Next slide. Thank you.
Wonderful job, Emily. Do we have any questions virtually for Emily?
Hi, this is Ira. I have a question, but first a comment. I really like the way you talked about data quality. It's something that if you don't pay attention to, your models and your prediction will be wrong. So the fact that you get data and you have to clean it up, that's such a big thing in all of this learning. So the question I had was, so your imputed data, how did you fill up the gaps for those? How did you do you think that method of how you completed the data was responsible for the lower accuracy?
Yeah, so we used a separate function to impute the data, and it basically took the average of all the values in that specific variable, and if there was and if there was something missing from the variable, it would put in the average. So it's possible that that was what lowered the accuracy so much, because so many of the imputed objects were true planets. And I didn't mention this earlier, but in our original data set, 50% of them were false positives. So having so many false positives in the training set would have an impact on the average values of each variable.
And that's the reason you chose to actually look at the imputed data, because you could just say, I'm not going to consider these, but you wanted to improve the accuracy of the whole data, is it? Is that why you looked at the imputed data set?
Originally, we just like took out we took out objects that had missing data. But like later on, we wanted to investigate how like what impact that those objects would have on our algorithm, and we found that it actually lowered our accuracy. So then we separated it to see how exactly it was affected.
Great work. Thank you.
Thank you.
Great, wonderful job.